We're now in chapter 7 of Further Pure 1. We're looking at methods in calculus. This video is going to lead on to and explain Leibnitz's theorem, which is an extension of product rule in a sense. It's what happens if we apply product rule repeatedly and we pay attention to the overall effect of that and try to simplify, spot a general pattern, which means we need to start with product rule itself. Hopefully you remember how this works. The product of two functions, in other words, if you've got two functions multiplied together, if you want to differentiate that, you need to write down one function unchanged, multiply it by the derivative of the other, and then vice versa. You add the two things together, u dv by dx plus v du by dx will give you dy by dx, the derivative of the product. It's easier possibly to write it using the dash notation, where y dash represents the first derivative of y, so that will give us uv dash plus u dash v. For example, we know how to differentiate x squared and we know how to differentiate sine x, but product rule will allow us to differentiate x squared multiplied by sine x. We get something like this. Notice that the x squared is variously differentiated or not, and the sine x is either differentiated or not, and we alternate. So you either have x squared in its original form multiplied by the derivative of sine x, or you have x squared differentiated multiplied by sine x unchanged. Once you're happy with this, you should be able to calculate a few of these just to check that you remember how this all works. There's a few examples for you to try. I recommend you pause the video, you have a go at these three. Okay, here's what we should get. E to the x multiplied by the derivative of cos plus e to the x multiplied by cos. We can simplify this slightly as well if we want to. For the next one, ln x differentiates to 1 over x, and x to the 4 differentiates to 4x cubed. We can put these together following product rule, and again we can simplify a little bit. Things work out quite nicely because the 1 over x cancels out partly with the x to the 4. The last one, although the functions involved are the simplest, is probably the messiest one to do with product rule. I've left it in almost as a warning that product rule, although it will allow you to deal with the product of two functions, is normally best reserved for situations where the two functions don't play nicely with each other. If there is no easier way to do it, then use product rule. In this case, it will be quicker and simpler to expand out these brackets, I would imagine. In fact, you could do even better for yourself by pulling out a factor of x, perhaps, expanding the rest, and then you've got a much simpler product to work with. You'll see that this whole thing does simplify down at the end if you apply product rule, but it's a bit of a mess. If you want more practice with product rule, I recommend you head back to the Pure Year 2 textbook. You want chapter 9, look at exercise 9D. So, what happens if we need to apply product rule again? This usually happens whenever we're trying to compute the second derivative if we needed product rule in the first place. So for instance, if we start with x squared sine x and we differentiate, remember this happens because we either leave x squared unchanged or we differentiate it, and at the same time we either differentiate or leave unchanged the sine x. Now if we were to do this again to get the second derivative, we'd need to do the same thing all over again with each of those two terms. Now we not only have a product rule problem, but we have two product rule problems added together. So the second derivative will end up looking something like this. If you follow it through carefully, you'll see the x squared cos x term. That ends up giving us x squared and 2x. The cos x gives us a minus sine x and the cos x. So the first two terms in the second derivative come from the first term in the first derivative. And then the last two terms that we see here from 2x unchanged or differentiated, from sine x differentiated or unchanged. But perhaps you've noticed something about the structure of this. In fact, if you follow the arrows down, you can see that the cos x terms that we've got in those middle two sections, they come from either sine being differentiated and then not, or sine not being differentiated and then being differentiated. And the order in which that happens shouldn't make a difference. The same thing happens with the x squared and the 2x, so we basically end up with the same terms in the middle. The very first term has an x squared exactly the same as the original function at the top, And the very last term has got a sine x. So the first term is the same as this. The last term we can see here is the same as this one. But then in the middle, we've got various other derivatives of those functions. So there's an x squared, there's a 2x, there's a 2. There's a sine x, there's a cos x, there's a minus sine x. And then the grouping together that happens with these two, we can simplify in this way. I'd like you to have a go at finding the second derivative of x to the 4 e to the 3x. You'll need to follow a similar pattern, use product rule, and then use product rule again. And then pay attention, just like I've done here, to the overall structure. So perhaps avoid the temptation to simplify too much at each stage. With ours, we could probably have made our job a little bit easier by taking out a factor of x once we found our first derivative. But I'd like you to have a go at doing this without doing that. Try it the long way and see if it can tell you anything about the overall structure or pattern you're going to end up with. Pay close attention to those middle two terms. Okay, here's what I get for my first derivative. Either leaving x to the 4 unchanged or differentiating, either differentiating e to the 3x or leaving it unchanged. And then the second derivative, it's a little bit messier, but we have x to the 4 times 9e to the 3x plus 4x cubed times 3e to the 3x. And then we also have another 4x cubed times 3e to the 3x along with a 12x squared e to the 3x. Look carefully at the different terms in here and you'll see the original expression had an e to the 3x. That appears in a few different places in our second derivative. Here differentiated, and here differentiated again. And at the same time, x to the 4 is going to appear in a few different places. Here differentiated, and here differentiated again. Now, since we've got our first and second derivatives, it might be worth pointing out what we can do with them. Remember, these can be simplified, so if we write them in their simplest form, dy by dx turns into this nice factorized expression, and the second derivative also turns into a fairly nice factorized expression. This gives us a graph that looks a bit like this, and we can see the various points indicated on there. These represent the turning points and the points of inflection. We can find turning points by setting dy by dx equal to 0. So obviously we've got one at 0 and one at minus 4/3. They're in blue. And we've got points of inflection anywhere where the second derivative changes sign. And the points of inflection we've identified, the first two red points are points of inflection. The next red point, actually the second derivative is 0 at that point, but it doesn't change sign. So technically that's a minimum point as opposed to a point of inflection. But it's one of these minimum points where we have a repeated root even within the first derivative. So it's a slightly different situation to normal, but we can see all the points where the first or the second derivative are 0 marked on this graph. Just for perspective, this is what the curve looks like if you zoom out a little bit more. So what we're looking at is just the small wiggle before the e to the 3x part of the function completely takes over and the graph shoots off towards infinity. Now, if you perhaps spotted a pattern with the previous two examples we worked through, and you're wondering if that applies more generally, the best way to find out is to work with a more general case. So what we're going to look at next is y equals uv, where u and v are just functions of x, and we're not going to specify which functions. We're not going to get bogged down in the detail of exactly what functions we're supposed to be differentiating. We'll just call them u and v, and we'll refer to their derivatives as u dash and v dash. So let's start by finding the first derivative. This is essentially restating the product rule. So we have u multiplied by the derivative of v and v multiplied by the derivative of u. Then we're going to take each of these two separate terms in turn and apply product rule once more. We get this. So if we leave the first term unchanged and differentiate the second, uv dash becomes uv double dash, the second derivative of v. And then if we take the same expression, uv dash, and we leave the second term intact, v dash, and differentiate the first term, we get u dash v dash. We do the same kind of thing with this one. we either leave the v intact or we differentiate it, and at the same time we either differentiate or leave intact the u dash. We get v u double dash and v dash u dash. But if you're paying close attention, you'll notice that two of these terms are actually the same. U dash v dash and v dash u dash. They might be written in a different order, but they're the same term. So we can put them together. U v double dash plus u dash v dash times 2 plus u double dash v. This might remind you of binomial expansion, and so it should. In fact, if we go one step further, it'll be even more reminiscent. When we find the third derivative, I'm going to use my simplified form for this one, but we're going to see how things combine. Now what we have is u v double dash gives us these two terms. The 2u dash v dash is going to give us 2u dash v double dash plus 2u double dash v dash. And finally, we have u double dash v giving us these two terms here. But again, if we look carefully, we'll find that there are some similarities in here. So we've got u times v triple dash, and that's the only instance of that one. But then u dash v double dash, that also appears here. U dash v double dash, we've got two of them. And u double dash v dash, that one also appears at the end. We have two of them and then one more. So we can simplify this as well. We have a single copy of that first term, then we have 3 and 3 and 1. So the patterns we're looking out for here are 1, 2, 1 and 1, 3, 3, 1. See if you can figure out what the fourth derivative of uv might look like. Make a prediction, give it your best guess, and if you want, you can work through and see if you're correct. In general, this is what we've managed to demonstrate, or at least we've started to. We've shown how it works for the first couple of derivatives, at least. This is known as Leibnitz's theorem, and although it might look a little complicated with the summation symbol, essentially all it's telling us is that we can apply binomial to successive derivatives of these terms. We effectively think of the u and the v and their various derivatives, first, second, third derivatives, etc., a little bit like we treated powers of the two nomials in a binomial expansion. So if you want the third derivative, we want to think of the binomial coefficients 3 choose 0, 3 choose 1, 3 choose 2, 3 choose 3. That's where we got our 1, 3, 3, 1 from. And we want to combine those with ascending derivatives of one of our functions and descending derivatives of the other one. Which one's which doesn't really make a difference. We can decide for ourselves which one's going to be easiest to think of as going up and which one's going to be easiest to think of going down. The binomial coefficients are symmetrical, so it won't make any odds. Just note here my notation to make life a bit easier. I'm using a number that looks a bit like a power, but I'm enclosing it in brackets to distinguish it from what you might think of as either applying a function repeatedly or a power of a number. When I write y to the power of n in brackets, it refers to the nth derivative, dny by dx to the n. So now let's have a look at how we can make use of Leibniz's theorem. There are a couple of different ways that this is used and a couple of different things you'll be examined on. The first one is essentially finding some slightly higher order derivatives without having to apply product rule directly a bunch of times. One thing to watch out for here, which I very nearly did when I first started working through this example, is that the 0th derivative of u, you need to remember, means just u. Just like if you don't differentiate y at all, you still have y. So watch out for that. Y to the power of 0 you might think of as 1, but in this notation I'm thinking of y to the power of a 0 in brackets as being the 0th derivative, so it's just y as opposed to dy by dx. Another tip for you. This will really help with the structure of your layout. You're going to need various derivatives of u and v. So if we're looking for, say, the third derivative of something, you're going to need the first, second, and third derivatives of u and v. There's no getting around that. You need all of the derivatives and ascending derivatives of one of them and descending derivatives of the other one. So you're going to need to write them all out. What often helps is that you write them in a table, and then you have the binomial coefficients alongside, so you can then just combine them at the end. I'll show you how I normally lay this out. If I want the fourth derivative of x to the 4 e to the 3x, that was the expression we were working with earlier, it'd be a bit of a pain to have to go through all 4 steps. But what we can do is start listing the derivatives of each of these two functions. So for u, we have x to the 4, and then the first derivative, second derivative, third derivative, and fourth derivative. And then for e to the 3x, we can do the same, but because we want the derivatives to be ascending for u and descending for v, or vice versa, I'm actually going to start my list at the bottom. I'm still going to work my way through the derivatives. I'm not going to try to jump to the fourth derivative all in one go, but I'm going to go backwards up this list so that I can actually calculate my derivatives in a logical sequence. The advantage of this now is that the derivatives are paired up in the way they should be according to Leibnitz's theorem. The first derivative is paired with the third, the 0th derivative is paired with the fourth, and so on. The last thing I need is the binomial coefficients. So you can either write these directly using Pascal's triangle for small sizes of n, which is fairly common, or you can use the more general formula, which we'll talk about later. The next thing to do is to combine them. So if you want, you can write this out. This is effectively a generalized version of, or it's rather a specific version of Leibniz's theorem when we want the fourth derivative, but it doesn't use my x to the 4 and e to the 3x yet. You can write it out like this if you want, or as you get more comfortable, you'll just be able to read off the values from your table. I'm going to plug them in. You can see, if you look carefully, the 14641 appearing there. We've also got the descending powers of the exponential and the ascending powers of derivatives of the other. So not so much powers of the exponential, but descending derivatives. We've got 81 e to the 3x, 27 e to the 3x, 9, 3, and e to the 3x. At the same time, we're seeing x to the 4 going the other way. So x to the 4 and its derivatives going along like this. The only other numbers you're seeing in there are the binomial coefficients, 1, 4, 6, 4, and 1. This can, of course, be simplified. So if you spend a bit of time on it, you can turn it into something that looks more like this. It's got a factor of e to the 3x because every single derivative of e to the 3x, no matter how far you go, will have a factor of e to the 3x. But also the rest of it can be sorted out. We can even pull out a factor of 3 and we get this quartic expression in front. I think you'll agree that although it is a bit messy, it's a lot quicker to do this than it would be to attempt to differentiate 4 times, simplifying along the way, or not simplifying along the way. Either way, it's going to be worse if you have to do it the long way than if you're able to apply this method. Worth mentioning here that Wolfram Alpha can help you out with this. All you need to type in is something like fourth derivative of. So while you're revising this and practicing questions, you can check your answers pretty quickly by typing it directly into Wolfram Alpha. It also gives you this fairly nice simplified form that looks a lot like the version I've got here. Now you can have a go at some questions from exercise 7a in the FP1 book. I suggest questions 2, 3, and 4 are a good start here. Now I said we could use the rule in 2 different ways. The second way is to find a general formula for the nth derivative. That may sound like I'm just restating what we just did. We just used the formula to find the fourth derivative, but we're talking about a formula involving n. So an expression that you could just substitute a value for n in. It's a single formula that should look simpler than Leibniz's general formula, so hopefully something that doesn't involve summations, but one where you could substitute n equals 3 or n equals 20 into it and find the relevant derivative. We're going to have a go for this one. We want to find an expression for the nth derivative for y equals x squared e to the 5x. And there's a little clue in here as to what's going on. It says we want to find an expression for the nth derivative provided n is greater than 2. Ask yourself what you think will happen to these functions if n is greater than 2, and that might give you an inkling as to why we're able to find a simplified version of this. Turns out the key thing is that one of your functions needs to eventually differentiate to 0. In other words, if you differentiate it enough times, you get down to 0. This might remind you a little bit of binomial expansion. If you do binomial expansion with negative powers or fractional powers, then you get an infinite expansion. But if you do it with positive integer powers, eventually the terms end up all being 0. In other words, there's a finite expansion. Beyond a certain point, all the terms are 0. Like a terminating decimal, 0.1250000 is an eighth, and 0.142857 recurring never quite finishes. We're looking for something that does terminate, so we can write a simpler version of the expression for it. And it turns out that because x squared eventually goes down to 0, we can have u dash, u double dash, and by the time we get to u triple dash, we've got to a derivative of 0. Because that happens, beyond a certain point, there won't be any terms in our expansion. And all we'll need to do is evaluate the first few and say, all the rest are 0. So what we can say here is that the kth derivative will be 0 for all values of k that are bigger than 2. And that's why they've had the condition n is greater than 2 in there. Now, what we're going to need for the e to the 5x is the descending derivatives. It's important that we have the ascending derivatives of u, because it doesn't make sense to start at the other end for u. We need to start at the end that we've got, and then it'll eventually go to 0. But that means we will need to know what the nth derivative of e to the 5x is. Luckily, we can kind of start down at this end, wherever this end happens to be, and then think about what's going to happen as time goes by. And eventually, we'll end up at places like this. You can see the pattern. The first derivative is 5e to the 5x. The second derivative is 25e to the 5x. And we can see how to incorporate that formula into the nth derivative, 5 to the n e to the 5x. And from there, you can work out the n minus 1th derivative and the n minus 2th derivative. When we combine those with some handy formulae that we steal from the binomial coefficients, we can end up with our nice formula. Remember, n choose k is just n factorial over k factorial n minus k factorial. And from that, you can generate some much simpler expressions that don't involve the factorial notation or the choose function notation. In particular, n choose 2 is quite a useful one to be familiar with. It should remind you a lot of the sum of the numbers from 1 to n. It is in fact the sum of the numbers from 1 to n minus 1, because we've got an n times n minus 1 over 2 instead of n times n plus 1 over 2. But you can generate it directly from the general result for n choose k. And if you get those, 1n and n times n minus 1 all over 2, that can be combined with the ascending derivatives of u and the descending derivatives of v. This is what we end up with. So our binomial coefficients over here are represented by the 1, the n, and the n over 2 n minus 1. The values of u, you can see in there, are the x squared, 2x, and the 2. And finally, 5 to the n e to the 5x, 5 to the n minus 1 e to the 5x, and 5 to the n minus 2 e to the 5x. Those are the derivatives of v that ended up appearing. We can, of course, simplify this a little bit as well. There are a few ways to do this. I've decided to pull out 5 to the n minus 2. You could even write 1 over 25 times 5 to the n, multiplied by that stuff. But we can see now that for any value n, we're going to get a number at the front, which depends on n. We're going to get a quadratic inside the bracket with the x and the constant terms dependent upon n. And then we'll have e to the 5x. So beyond a certain point, the derivatives of this function all behave in a similar way. The details will change as n changes, but the overall pattern will not. It's going to be a quadratic multiplied by an exponential function. Here's a handy tip. It's not particularly quick and easy, but if you are getting in a muddle with the nth derivative problem, try perhaps the base case or the first case that you can. If the rule needs to be true for n greater than 2, we can test out n equals 3. Just try differentiating 3 times, like we did with the previous examples, and see if what you get matches what we've got here. If you want to try it out for yourself just to check an answer without necessarily being in exam conditions, feel free to go to Wolfram Alpha and ask for the third derivative. and then compare the answer on your screen with our expression here for n equals 3, and you should find that they match. Now you can have a go at question 5 from exercise 7a. This works through a very similar process with just a slightly different question. The last example I want to look at involves fractions. Now if you just wanted to differentiate this once, you'd probably use quotient rule. But quotient rule is itself just a consequence of product rule and chain rule. So there's nothing stopping us from breaking this apart into the product of two functions. And as you can see, one of them is going to be a fraction, so you might want to think of it as 1 plus e to the 2x in a bracket to the power of minus 1 to make it easier to work with when we're differentiating. Let's start with the easier of the two. We have the derivatives of cos, and then we start with v. This is going to be chain rule, so we need to think bring the power down in front, reduce the power by 1, but then also multiply by the derivative of what's inside. So 1 plus e to the 2x differentiates to give 2e to the 2x, and once we've got that, we can find the second derivative. But you might notice now we've got a product of functions. We've got the original bracket with a power of minus 2 now, and we've got the 2e to the 2x term. So we actually have to apply product rule. Once you do this, you get this delightful looking creature. You can see where the pieces come from. We've either got the 1 plus e to the 2x to the minus 2 bracket appearing as is or differentiated. We've got the 2e to the 2x either as is or differentiated in the alternate terms. But as you can see, we still need to do a third derivative. At this point, you might be thinking, haven't we got a theorem for this that will make it easier? And yeah, technically, you could apply Leibnitz's theorem to this v dash. You could apply it to the first derivative in order to find the third derivative. But it's only 2 steps further along. So although it may seem tedious, your best bet is probably to use some kind of compromise version. We want to use the idea behind Leibniz's theorem without necessarily going the whole hog and writing it out as an entire process. You can very easily get lost along the way if you're trying to recursively apply a process over and over again within a question. So this is what my third derivative looks like. And when I say go halfway, this is what I'm referring to. If you look carefully, you'll find that this first term here is what generates the minus 6 term at the beginning and one copy of this term in the middle, the 2 lots of the bracket to the minus 3, 4e to the 2x. But at the same time, this second term is going to produce the stuff at the end, but also one copy of the stuff in the middle. That's why we end up with 2 lots of that. So it's worth noticing that. It saves you a little bit of time as you work through, taking advantage of what we already know from Leibniz's theorem. Now, once you've got those, in order to start combining them in the right way, it's probably helpful to simplify slightly. This is a fair bit of work and it's going to be messy, but it is possible to turn each of these into a slightly nicer looking fraction. And it probably helps a bit if you can do that, because then you have a fighting chance of fitting your entire answer on one line, potentially. It looks a bit of a mess, and I'll be honest, it doesn't get much prettier than this. We have the binomial coefficients represented in purple, 1, 3, 3, 1. We've got v and its derivatives represented in blue, and then the trig part, u and its derivatives represented in green. And like I say, you can simplify a bit further. Here's a couple more alternatives that you might produce, depending on how you've gone about it, but neither of them are particularly elegant. They don't necessarily tell you more about the function than the original version does, so it's not necessarily worth the time and the effort that it would take to crunch through the extra algebra. But it's worth knowing that you can. And the main takeaway from this is that you can apply Leibniz's theorem even when you've got fractions, although it will tend to be a bit more hard work algebraically. It's worth setting your scene out carefully and having a clear structure, leaving some gaps between lines of working so that if you make mistakes or need to simplify things, you've got the space to do that. Now you can have a go at questions 4, 6 and 7 from exercise 7a.